Hello and welcome to this tutorial on building a convolutional neural network for the immense data using TensorFlow. In this tutorial we'll be using Keras API, which is a high-level API for building and training deep learning models. So first I'm going to start by importing TensorFlow, and just a little bit about this data set. It's widely used for image classification. It has about 70,000 grayscale images of handwritten digits. So that would be what we're doing right now, is loading into it. After we load into it, the next important part is pre-processing the data. So we're going to normalize the data by dividing each pixel value by 255. This helps bring all the pixel values within the same range and makes it easier for the model to learn. We will also reshape the data to match the input shape of our model. The reason for normalizing the data is to ensure that all values are in the same range. In this case, each pixel value is divided by 255 to bring the values within the range of 0 to 1. This is important because the model uses gradient descent, which is an algorithm to optimize the weights and biases of the network. If the pixel values are too large, the gradients will be large as well, leading to longer training times and potentially unstable learning. Normalizing data helps migrate these issues. The reshaping of the data is necessary because the model we're using requires a specific input shape. In this case, the input shape is 28 by 28 by 1, which represents a 28 by 28 grayscale image with a single channel. By shaping the data to match the input shape, we can ensure the model has the correct data format to start learning. So that's what we're doing right now, is I'm typing in to divide them by 255 to get them under a value of 1. In this portion, I'm just going to reshape the data to the 28 by 28 by 1 that we had just talked about. So while I'm typing this out, I'll explain a little bit about the sequential model we'll be using. So it's using Keras API that'll help us recognize patterns in images. The model has several layers to process the input image, each serving a specific purpose. There's a convolutional layer, which is conv2D, and it detects the features in an input image. There's a max pooling 2D layer. This reduces the size of the feature maps to make the computation faster. Then we flatten layer, converts the output from previous layer into a one-dimensional vector. The dense layer uses the features learned by previous layers to make predictions. And so just a little bit more for the convolutional layer. It performs a convolution on the input image that is a mathematical operation that is applied to the image to detect specific features in the image, such as like extra edges, textures, and shapes, and different things like that, kind of like patterns and such. And each filter generates a feature map that represents the feature detected by that filter. So the convolutional layer is pretty important. There's also the max pooling layer, and then the flatten layer just flattens the data into a one-dimension input. And the dense layer is just a fully connected layer that is for making predictions on the previous layers. So I put 10 here because the output is from 0 to 9, which is 10 characters. So in other data sets you might have more or less. So the next part of this is compiling the model. We'll do that by defining the optimizer, loss function, and evaluation metric. The optimizer is responsible for updating the model parameters based on the loss function, and the loss function is used to measure how well the model is doing in terms of accuracy. In this case, we'll use the atom optimizer, sparse, categorical, cross entropy loss, and accuracy as the evolution matrix. And I just copied that from a different file just because it's easier. Little, kind of get the spelling mixed up every now and then. So this is the fit. This is us training it. And during the training process, the model will learn features of the input images and make predictions based on that. And now we're evaluating the model. Once the model is trained, we'll evaluate its performance on the test data. We will use the evaluate method to get the test loss of the model. And then for making predictions, we will use the model to make predictions on some images and visualize the results. We will use the predict method to get the predictions and the argument function to get the predicted class for each image. And of course, there's going to be two other parts to this where we're going to use this model. So we're going to want to save it as well. And so if you watch my future videos, you'll be able to just go straight off of that and just use this file that we're about to create. So right here is when we're saving it. We're going to save it as model.h5. And we're doing this, and it'll pop up on my left here. After we run it, of course. And so now what I'm doing is I'm getting ready to plot the images. And this is just using the matplotlib that we imported earlier, and that's why we're importing it. Yeah, so I'm just trying to figure out what I did wrong here. I think I'm just gonna take this whole thing out and just copy from a different file real quick, just because I know it works. And I'm not as great with matplotlib, I suppose. So, okay. So I didn't actually load the file, as you can see here. So we need to do that. Also, my recording's off by a little bit. I'll fix it in a second. Okay, so I got that fixed, and here is what outcomes from this. So we have 4, 0. We have, what's the next number? It's going to be 1, predicted 1, true. 2, predicted 2, 7, predicted 7. And there you go. That is how we make the model, and we saved it so we can use it for later videos. That's pretty much it to this. Like I said, I'm gonna try and get a video to use your camera on your screen as well as pictures downloaded from the internet to use this model on. Thanks for watching, and I hope to see you next time.